We're now going to extend the idea that you guys found out about division. And since division tells you if something is a factor, right? Like, let's say 6. 6 divided by 2 is 3. No remainder. That tells me 2 is a factor of 6, where 7 divided by 2 is 3 with a remainder of 1, so 3.5, and that tells me that 2 is not a factor of 7. So this key idea being that things that didn't have remainders were factors. Things that did have remainders were not factors. So division is not just a process that we learned, but something that can tell us if something is a factor. And then we've learned that factors can give us zeros, which can give us x-intercepts on the graph, which can help us sketch the graphs of some of these equations. So we want to try and put like how this process is related to all that other information that we've been working on. So first, I just want a vocab idea here. They might use the term synthetic substitution. So let me just be really clear that generally you guys, if you substitute 2 into a function, you take that function, I'm using the f of x that's here in our problem, sorry, and you substitute in 2. And then you finish this calculation. So let's see what this gives us. 2 times 16, 8, 3 times 4, and 5. So we're going to get here 32 plus 8 minus 12 minus 5. And that will tell us that f of 2 is, let's see, 40 minus 12 would be 28, minus 5 would be 23. Now, I want to show you something else. If 2 was the number in our synthetic division box, and we used this polynomial, so the coefficients would be 2x to the 4th, 1x to the 3rd, negative 3x squared, 0x, and minus 5. If you went through this synthetic division process, notice that what you get as the remainder is the same as what you got here. So there's a couple of things. Your remainder tells you if, so like with a 2 here, this could be calculating f of 2, or I could be wanting to know what I get when I divide by x minus 2. So this can kind of be used 2 ways. What I'm seeing is last lesson, we already found out that if I was dividing by x minus 2, my quotient would be 2x to the 3rd plus 5x squared plus 7x plus 14 with a remainder of 23. I'm now seeing that that 23 is not just some random number. It also happens to be the number I would get if I was plugging this exact value into the function. So that's just kind of showing you a different relationship, that the remainder when you divide by x minus 2 is the same number you get when you plug 2 into the function. So f of 2 is 23. What is f of x divided by x minus 2? We just talked about this. So we had a 4th degree polynomial. We would be dividing it by a linear function of the 1st degree. So this would be a cubed term, squared, linear, constant, and remainder. So our answer here to the division problem, our quotient, would be 2x cubed plus 5x squared plus 7x plus 14 plus this remainder of 23, and we were dividing by x minus 2, so that looks like 23 over x minus 2. Part C, what is the remainder when f of x is divided by x minus 2? It is 23. So then these questions, is x minus 2 a factor of f of x? In order to be a factor of something, when we divided by it, it would have no remainder. This division had a remainder, which means x minus 2 is not a factor of f of x. Then it asks, is 2 a 0 of f of x? Remember, a 0 comes from a factor. If x minus 2 was a factor, then yes, 2 would be a 0. Since x minus 2 is not a factor, then no, we're not going to get a 0 at 2. And part F is just another way to ask this question, making sure you guys are remembering that we can ask this several ways. Is 2 a solution of f of x? No, because solutions is another word for zeros. Okay, so this is how this information can help you with some of the information we were looking for before. So when we look at example 13, so first it says use synthetic division to divide this by this and use our work to answer the question. So for this synthetic division process, -2 would be our value in the box because that would be the 0 of x plus 2. And our lead coefficients would be 1x cubed, -1x squared, -10x, and -8. So if we do the synthetic division process, here's what we get. And then we have to be able to interpret this, right? So what is f of -2? Well, remember, we just found out that substituting in -2 is the same as the remainder when we do this division problem. So it would be equal to 0. Is -2 a solution of f of x? It is, because if we plug in -2, we are getting 0. That means -2 is an x-intercept, it's a 0, and it's a solution. So yes, it is. Is x plus 2 a factor? Yes, x plus 2 is a factor because this synthetic process is showing division by x plus 2 when we're using a -2 in the box, and it had a 0 as a remainder, which means it is a factor of that polynomial. Part D, what is f of x divided by x plus 2? That's asking for our quotient or our answer. And in this case, we should be getting a quadratic. So we would have 1x squared, or x squared, minus 3x minus 4. No remainder, since it is a factor. Now it's asking us to rewrite f of x in factored form. So here's what you know. You know that x plus 2 is a factor. What was left after you divided by x plus 2 was x squared minus 3x minus 4. So we know that those two things multiplied back together would get us back our original polynomial. So this is one way to factor it. And then the question is it completely factored? Are we done? So we can factor this polynomial a little bit further using any of your quadratic factoring methods. And we'll get x plus 2, x minus 4, and x plus 1. This is the polynomial in its completely factored form. So another perk to this division process is that if we know something's a factor, we might be able to factor something that before might not have seemed factorable. Then the question is, what are the other zeros besides -2? So they've already acknowledged -2, which we would get from that factor. So our other zeros are the other solutions that we would get from the other factors in the factored form of this polynomial, which would be 4 and -1. So make sure you understand that this polynomial has 3 zeros, or 3 solutions in total, but they already acknowledged the first one, so I only was listing the other 2. All right, and then lastly, we're going to try and sketch this function using those zeros. So let's pay attention to what we are actually sketching. So if you look back, this is a cubic. So shape-wise, we should be thinking something like this or like this. And then we need to understand the lead coefficient to decide the directions of the end behaviors. The lead coefficient was positive for this function. So not this direction. We're going to go with that the right side goes up towards infinity and the left side goes down towards -infinity. Then we need our zeros. So we have -2, -1, and 4. So I'm going to mark those on my graph. And then the last thing that your sketch had to be correct in is the behavior at those zeros. These are all single zeros. None of them had a factor raised to a different power, so they didn't have any multiplicity. So I just want to make sure my function goes from having a -infinity end behavior on this side of the graph to a positive infinite end behavior on the other side, and has those couple of turning points and uses the zeros present. So there we go. And yours might not look exactly like that. Remember, we're just looking for correctness in shape, end behavior, zeros, and behavior at those zeros. All right, so now we're going to look at one application problem in this sense. So they give us a polynomial, and they tell us it expresses volume in cubic inches of a box. So what I know about previously of volume of a box is I would multiply length times width times height to create that volume. So this polynomial was created by a length times a width times a height of the box. Then they tell us the length is x plus 5 inches. So right now we know x cubed plus 9x squared plus 23x plus 15, that's the volume, was created by the length, which is x plus 5, times the width, which we don't know, and times the height, which we don't know. And they want us to find those other two dimensions of the box. So they want us to find width and height. So I don't really know where to start, but I can see that I'm getting like a factored form of this polynomial on the right side of the equation. And I know that x plus 5 is one of the factors. So I'm going to refer back to the previous problem we did. We basically did this. We went to write it in factored form. We knew this was one factor. We did division to see what the rest looked like. So I'm going to start with that. I'm going to take my volume polynomial. So I'm writing its coefficients because I'm going to use synthetic division, and divide it by the length. And then I'm going to go through that synthetic division process. And this is super important. If I didn't get a remainder of 0 here, I would feel like the problem was written incorrectly or I made an error, because x plus 5 is supposed to be a factor of this polynomial, given that it's one of the factors that created that polynomial. So what I figured out here is if I divide the volume polynomial by the length, I get this result. That was a cubic divided by a linear function, so this should be a quadratic. So what I have now is that I know x cubed plus 9x squared plus 23x plus 15 is made from x plus 5 specifically multiplied by x squared plus 4x plus 3. But this is the length, or excuse me, not the length, but the width and the height multiplied together. So can I break it up? And we have quadratic factoring techniques that allow us to factor that quadratic as x plus 3 times x plus 1. So I don't know which one is which, but I know my other two dimensions are x plus 3 and x plus 1. Those will be the width and the height.